Hello and welcome to this talk about k8gb operator for Kubernetes. Before I start, let me briefly introduce myself. My name is k8gb and I work as a software engineer on this open source project. Before joining APSA where I currently work and the k8gb was originally created, I also worked nearly 8 years for Red Hat and shortly for Oracle. Today I'm gonna be talking about cloud native Kubernetes global load balancer with name k8gb. I joined the project about half a year ago, and the core team currently consists of 5 developers. Let me open the talk with a simple animation that I've prepared so that you have better understanding what I mean by rather abstract term cloud native global load balancer. Then I'm going to describe the components of the system, and then we will spend most of the time on a practical demo. So let's start with a simple animation that will explain the high-level functionality of k8gb. Imagine we have a Kubernetes cluster with a web application deployed in it. It consists of two pods and users who can communicate with the application using HTTP protocol. Now, if an accident happens and the application goes down and Kate is not able to recover the application, it negatively impacts the user experience because the application is no longer reachable. Let's see how k8gb can help here. k8gb operator makes only sense in multi-cluster environments, so let's spin up a new cluster. Using Helm chart, install the k8gb operator in it, and last but not least, configure the k8gb to use the HDNS server. In our example, it's going to be using Route 53, which is the default DNS solution for AWS. In our example, we configure the HDNS server to work as a recursive DNS server and delegates all the requests for our domain, example.com, to one of our internal core DNS servers. This is internally done by introducing so-called glue record. The role of k8gb controller here is to update the A records for our internal core DNS servers in accordance with the load balancing strategy. For the sake of simplicity, let's pretend the k8gb can make those DNS updates directly on the HDNS level. Note the TTL is set to relatively short value, in our case it's 30 seconds. Now let's take a look how the failover strategy works. As before, our user communicates with the web application. First, they ask Route 53 to resolve app.example.com, and for the next 30 seconds is going to be IP of a node from the cluster in Europe. Having the hostname resolved, they happily communicate with the application until the failure on EU cluster happens. Luckily, this time k8gb controller will save the day and change the DNS record to point to the healthy cluster in US. Tooks may not see the switch immediately because of the nature of TTL in DNS, but it will be switched eventually. Once the cluster in Europe is fixed, perhaps operations can add another node, the k8gb controllers know that the EU was set as a primary cluster and will redirect all the communication back to the cluster in EU. In the animation, we have shown that the TTL was set to 30 seconds, so in the worst case, the user would have to wait for 30 seconds to see the switch, but the value can be set to something shorter. In that case, the switch would be more immediately done, but on the other hand, it would affect the DNS caches, and the user would have to ask more frequently for DNS resolving. So it's kind of trade-off between those two qualities. And the animation was created in framework Manim and is available on this link. In the animation, the representation of k8gb was kind of oversimplified and it was all represented as the red septagon. But let's look more into deep into those components, what they are and what they do. It consists of core DNS, external DNS, and the controller itself. The first two are well-known open source projects. Everything is bundled together and deployed by Helm chart. For core DNS, my colleague has developed our own plugin that's based on Case external plugin and is able to work on top of this DNS endpoint resource. And we use core DNS itself for internal DNS resolution. It works as an authoritative server for our internal DNS records. And because of the hierarchical nature of DNS, we can use the HDNS server to work as a recursive server and this internal core DNS server that needs to be deployed in each cluster as an authoritative server for their own domains. Another component in the picture is external DNS, and we use it for updating the external HDNS servers. They support majority of cloud providers, be it Route 53, NS1, Infobox, and like numerous others. It also works with DNS endpoint custom resource, and we also update TXT record on the HDNS server by each controller to represent heartbeats from our controllers. This is done because to prevent the split brain scenario where each operator needs to report itself as healthy, and if it doesn't update itself for a predefined time, it's considered as broken. This can answer the questions like what will happen if somebody unplugs the electricity in one data center altogether. And the last thing in the picture is the k8gb controller or operator. It's written in Golang. That's where we contribute the most. It acts upon the GSLB custom resource, or alternatively, it can also work with annotations on ingress resources. So if the annotation has some predefined key on it, it will create the GSLB resource for you. It's based on the operator framework, operator SDK, which is itself based on KubeBuilder, and the project was started by Yuri Tsarev. Now let's get practical and see k8gb in action. So to run the local development cluster, I have to run this task, deploy full local setup. It's gonna take about 3 minutes, and you can replicate it by going to our website, and you need to first install some prerequisites like Golang, Docker, kubectl, Helm. We use k8gb for spawning new clusters, and you basically can follow this tutorial, but I'm gonna show something more advanced in my demo as well. So let's wait for it. Alright, so the setup has finished, and it actually installed 3 Kubernetes clusters, 2 working ones and one merely for DNS, HDNS server. In the working clusters, there are things like ingress controller, in our case is Nginx, demo application that will simulate the load, and our operator or GSLB custom resource definitions, and of course our operator. And yeah, actually let me show you what's in the HDNS cluster. This is a fairly simple one. There should be only 2 pods running, and this one belongs to a bind server running in Ubuntu, and this simulates the external DNS server. So if I switch back to working, actually I can communicate with the DNS server as well using the DIG. It's listening on a localhost, so if I do this thing, it will return those 2 IP addresses, and this actually pertains to nodes from cluster in EU. Let me verify that. If I switch back to cluster 1 and list all the nodes, these 2 IP addresses are the same as these 2. I can also do not failover but round robin. That's another load balancing strategy that will randomly select the IP of each node same likely and return the IP. So in this case we are returning 4 records because the 5 and 6 pertains to nodes from another cluster. I can convince you by doing this. These 2 IPs are from the other cluster. So let's see what's actually deployed in the working cluster, there should be a couple of CRDs. So if I do this, we can see that these DNS endpoints and GSLBs are used by the operator. This is for communicating the DNS records to external DNS and to core DNS. And this one is to set up the operator to do his job, basically, to do either the failover strategy or round robin strategy. I can show you a couple of those. Oh, I should have something like this to list in all namespaces. And as you can see, there are two load balancing strategies up and running. One is failover, one is round robin. That's why we saw this working. And now I can deploy a demo application simulating the load as we saw in our animation. And this will basically do simple HTTP calls. First, I'll be doing basically this make follow goal target. It will run this container with a couple of environment variables set and two arguments. First one is this thing that will be evaluated to, missing a quote here, to this IP address, and the other one that will be just a host name. This IP address is the one that represents the internal core DNS server. If I list all the services in all namespaces, you can see that we have k8gb core DNS service with the same IP. So we are passing these two arguments to this container. Now I'll show you the bash script that's actually running in this container. It's in the deploying test apps little demo. Yeah, this is the bash script that will be run inside the container. And as you can see, it takes two arguments. One is the name server, so the IP is the IP of name server of the internal core DNS server, and fully qualified domain name. In our case, it was this IP or this host name. So, and what it does, it actually puts the name server under the /its resolve conf, and then in a loop, it will try to communicate with the application using the DNS server. It will try to resolve the host name, and it will sleep for, I think in our case, it's 5 seconds. So let me do that. Now it's gonna download the image and deploy it in our cluster. And we should be, or we are also grabbing the message from the response, so we should be able to see the response is coming from our demo application. It's simple application called podinfo, and it's returning the tag of the cluster. In our case, we have two working clusters, and one is tagged by mark EU, and the other one is tagged with the mark US. I think the cluster 1 is EU and cluster 2 is US. So we are simulating some loads on our cluster. Now I will demonstrate the failover strategy by simulating the incident. So let me split the screen. And k8gb is nice because it uses the readiness probe on each container. So once the readiness probe fails, it will identify the deployment as a malfunctioning, not healthy, and will do the switch. So we can either break the readiness probes not to pass, or which is easier thing to do, we can scale down the deployment to 0, and it will be considered as unhealthy. So let me check I'm on the correct cluster. This one is as the primary one, and I will scale the deployment. Actually, let me first list all the deployments so that I have the correct name. It's this is the front-end podinfo is the demo application we are hitting from this curl. So if I scale it to 0 replicas. Scale deployment, and the namespace should be specified as well. So we scale the deployment to 0 replicas on the EU cluster, and we are hitting one issue, one error in here, but the switch has happened in here, and right now we are communicating with the US cluster. So as you can see, the TTL was still set, it was still hitting the EU cluster, but then the switch eventually happened. But the first cluster was still marked as a primary one. I can actually show you the GSLB, which is in there. It's this one, the failover. It should be the correct namespace as well. Failover. Oh, the name is this. So as you can see, there are two IPs. We have a status field on the custom resource where we put those information that should be, or the correct IP addresses that should be resolved under this host name. And as you can see, there is a primary, where is it? Primary geotag is set to EU, and geotag of this cluster itself is EU. So we are returning these two IP addresses as a resolution for this host name. But we have two clusters, one is tagged with EU and the other one is tagged with US. And once the pods on the EU cluster are healthy again, we'll be returning the IPs from EU clusters. So let me try to do that. I will scale again the replicas on EU clusters back to 1. And we should be able to see the switch again from US to EU, because, and this time there shouldn't be no failure, because we're switching from healthy cluster to another healthy cluster, which is like safe thing to do. Again, we are waiting for TTL to expire, and then there we go, we are hitting the EU cluster. So that's the failover strategy. We can also be hitting the round robin endpoint, and then we would be like randomly choosing the between the clusters that can help spread the load between a couple of geographically dispersed locations. Now, to better visually see what's happening during the switch, I've also prepared a makefile target that will deploy Grafana and Prometheus, and we can see the metrics coming from this demo. To do that, I will need to deploy two Prometheuses, one in each cluster. Let's wait for this. So the Prometheus has been installed, and we also need to deploy Grafana. This time we will be deploying it only to first cluster, because there is no need to have it twice in there. And during the Prometheus installation, we marked two services or two pods with like scrape me annotation that will help Prometheus to understand what should be collecting. So let's wait for it. Right, so Grafana has been installed. Credentials are admin, and it will ask for change during the first login. Here it is. So it has been installed, and together with the Grafana itself, we also ship two dashboards. Only one is populated here. I think it will take some time to pop up. So this is like the default one for monitoring Kubernetes clusters. No data in here because it will take some time to appear. If I go back at here, it is the failover. It was created with the config map. And if I go here, we can see some traffic in our graphs, and there is traffic on EU cluster. We are hitting 36 requests per. It's not per minute. The PromQL query is set up to calculate this thing over 180 seconds, which is 3 minutes. I think it makes sense because we had the delay between the calls, 5-second delay between the calls, so it's like 12 requests uh, per minute, right? Times 3 is 36. And let me do the switch again, and we can see visually what's going to happen. So again, I'm scaling the pod info to 0 replicas on EU cluster, which is set as a primary one, and we should be able to see the switch. Okay, hitting the error twice in here, and it was switched in here. Now it takes some time for the aggregation to calculate correctly, I think it's correct calculating with some rate over this time period. So some of the data points should appear before it will plot the point in here. Here we have 0. Let's wait a bit. Right, and finally, after a minute or so, we can see the change. And if I actually zoom in, like for last 5 minutes, we can see that this is going down. It will go down to 0 once the time period has expired, and this will go back to 36. Yeah, so that was the visual demo of what's happening. The k8gb operator itself also exposed some useful metrics. So these metrics are actually coming from the podinfo application that has been done, that's scrapable in Prometheus format, and you can use these metrics. But k8gb exposes some metrics, some useful metrics as well, and you can monitor like how many GSLB resources are there, if how many endpoints we have, and things like that. So you can set up your monitoring infrastructure for your needs and be notified if something fishy is happening in your clusters. 36, almost 36. So yeah, that's it, and that sum up the demo. I'm gonna show also an example where k8gb is deployed in AWS. I've prepared 2 clusters, so let's check. There is cluster in EU West region and Africa South region, and the EU is set as a primary one and Africa is a secondary one. Again, those two work in a failover mode. So there is a GSLB resource in this cluster, and I can list it. And we can see the host is failover.test.k8gb.io. So let's try to hit this URL in browser. And we can see it's a set to EU West. That's the podinfo application again. And now if I scale down the deployment again on this primary cluster to 0, we should get a response from the secondary cluster. So first, let's make this all the deployments. That's the front end podinfo. So scaling it down to cluster, primary cluster should. Okay, we are hitting the issue because of the browser cache. So let me open the animals windows. It's not in my. That's the URL. Now we are hitting the Africa. So that's the switch. I can try to switch it back again. Scaling the deployment on EU cluster back to 1. which should switch the communication back to the EU cluster. No, still Africa. Browser caches are the worst, so let me try the first one. Yeah, there we go, the EU. Yeah, that's it. So yeah, I'll close my presentation by repeating that we have created DNS-based global load balancer. It's a Kubernetes native solution in a way that we rely on those customizable readiness probes, ingresses, and custom resources. We are more than happy to accept your contribution. So we are on Slack. You can reach us on Slack. And I've also totally neglected the part that we are suitable to work with GitOps together because we need to deliver this configuration in each cluster and it needs to be relatively similar. So GitOps is the thing to go and where it can shine. We have some examples with Argo CD. So yeah, reach us on Slack and thank you for your time.